Hello, everyone. Today we are starting to talk about Activity 6, which starts on page 77 in your Springboard books. And we're going to talk a lot about transformations of functions and talking about the graphs of even versus odd functions. Okay. So the first part here asks you to sketch the graph of a bunch of very famous parent functions. And what a parent function is, in its most simplest form, is the basic type of a particular function. So for instance, with quadratics, you see quadratics all the time where they're moved around because it might be like x squared minus x plus 2, but the parent function is just x squared. So I attached the handout, hopefully to the link to this video, hopefully I remembered that, that have these basic ones sketched out. Otherwise, you always kind of have that ability to sketch them out or graph them in your calculators to look at. Okay. Now from here, what we're going to talk about then is what happens when we start moving these around. So have this chart handy, and I'm going to kind of go through it so we could start testing these out to see which one matches with the other. So I'm just going to choose our quadratic as our parent function because I think it's a good one to start playing around with. And part A asks us if we put a value out front, an A value that is greater than 1, so let's say 4. What happened to our graph versus or when we type this in? Well, in this case, this is going to be a vertical stretch, right? We're stretching it up vertically versus if we have a value less than 1/4, like 1/4, where this is actually going to be a vertical compression. It's making it wider here. Okay, so for our first two here, we should have D and E taken care of. Okay, what happens if we change our graph, however, on the inside of it? Okay, so our graphs, if we take a B value that is greater than 1, so again, let's say 4, inside of that functional value, this time we have a horizontal compression. We're shrinking it horizontally. And again, if we take that value and we make it less than 1, we have a horizontal stretch. So sometimes it's hard to identify just by a picture what's the difference between, for instance, the horizontal stretch and the vertical stretch, or excuse me, horizontal compression versus a vertical stretch and things like that. And honestly, it takes sometimes just visually, you might not know what the difference is. It takes kind of playing around with the values inside, outside. Is this a horizontal stretch or is this a vertical compression? So, like I said, playing around with those. But again, this one inside, this is going to be our value of a horizontal compression, and then this one's going to be our horizontal stretch. So I always like to think about the horizontal ones are backwards because if you have a value of 1/4, you're not really thinking you're stretching it, kind of like we did with the vertical ones. But and the same thing with 4. You don't think about compressing it with 4 because you think that that's a bigger value. But horizontals, as we'll talk about with the rest of these, sometimes they're a little backwards. So those out. Now, the next two then are asking us to start playing around with either subtracting values inside here or on the outside of our function. So here, if we pick a C value, let's say 7, is it horizontally translated our graph, or minus -7, aka +7, translated it to the left, right? Remember, so that's going to be our horizontal translation. Versus if we put 7 on the outside, move up our graph here, let me see it. We have our vertical translations when it comes outside of the function. So we have horizontal translation, so H, and we have vertical translation C. And then our last two is what happens when we have that negated X value outside versus inside. Well, outside is a reflection over our x-axis versus inside is a reflection over our y-axis, which in the case of the x squared isn't going to really actually look like anything, but let's say this was x third, then you could see that flip over the y-axis, how it flips between the red and the green. So then we have, for outside here, this is going to be our reflection over x. And then when it's inside, it's the reflection over y. Now, we're going to skip the next page, but kind of moving on to look then at page 79. What's going on with each of these? Well, if you are adding 3 outside, this is a vertical translation, we said, and if we're multiplying by 3 on the outside, this is a vertical stretch. So what's going to happen each time here is these vertical movements are affecting our y values. So for both of these charts, notice all of the x values would stay the same, but what's going to change here is that the plus 3 here is going to make our initial f of x values add 3 units to it, right? Add 3 units, continues down the chart. Outside of here, this multiply by 3 is going to take those initial f of x values and multiply them by 3. So we'd have 512 times 3, 216 times 3, you get the idea, 64 times 3, and all the way down. So these vertical transformations affect our y values. And so you're probably on to guessing that our horizontal translations here and here are going to affect our x values. So in this case, what's going to happen is actually all of the g of x values are going to stay the same in both of these charts, but our x values are going to be what ends up changing. So again, because it's a horizontal translation, all these are the exact same f of x values. What will change, though, is what we are doing to our x values. So really what's happening with this too is, again, this is a horizontal change. So what's going to happen here is these are actually decreasing by 1/2, because even though we said it's kind of backwards whenever we affect our horizontals. So really these are decreasing by 1/2 our x values, because horizontal translations are a little backwards. So what's happening is these x values from our chart are now being cut in half all the way down here. And over here, again, these are a little bit backwards. We talked about how this plus 2 really is actually shifting it left 2. So all of our x values are really moving to our left each time down the chart. All right, finally, we have our reflections, right? We talked about this reflection out front here. This is going to reflect over the x-axis, aka you're changing your y value. So all these x values here will stay the same as the original, but our values here in the chart are going to change their sign because they are reflecting over that axis. On the flip side over here, we're changing the x value. So all of these values are actually going to stay the same here. But what's happening is in the second chart, we are reflecting over the y-axis, aka we need to change our x values location. So all of these now are going to flip signs, except for 0, because 0 just stays 0. And these all would change down the chart. Okay. So again, it's a little bit backwards. Number 6 is actually kind of what we wrote up here. When you're reflecting over your x-axis, you're really changing the y value. Reflecting over your y-axis, you're really changing the x value to flip on your function. Okay. We're also going to skip page 80. Let's just save us a little time, make this video not forever. And then finally, we're going to kind of end today talking about an even versus an odd function. Okay. So we have some examples here of an even function versus an odd function. And algebraically, to figure out if something is an even function, if you plug in f of negative x and it comes back to the original function, it's even. Okay. that's how you can find out if a function is even. So for instance, if we look at this quadratic here, x squared minus 3, if we plug in negative x, right, f of negative x. So I'm going to plug negative x in where I see x. Well, negative x squared is x squared. So because this came back to be the original function, these two match, this is even, okay? Visually then, how do we look at an even function? Well, I'm gonna go back to using Desmos here. If we type in x squared minus 3, if you have symmetry here to the y-axis, that is also going to tell you that this is an even function. So if you could fold this over the x-axis, this is an even function. Right, so that's another way of looking, or excuse me, the y-axis, that's another way of showing that that is even visually then. Okay. Well, what about our odd functions? Well, x to the fifth plus x is going to be an example of that, right? And talk about it, I guess, in a sec. But what happens here with odd functions is that notice when you plug in negative x, it equals the original function negated. So what I mean by that is if we test if this is initially even, we plug in negative x to the fifth plus negative x. Well, what's happening here is anything to an odd power, any negative to the odd power stays negative, and then minus x. So notice this is not the same as the original, so this is definitely not even. And then to test if it's odd, we're going to take the original function, and if we negated all of the symbols in the original function, so here was the original function, and if we negated both of these, notice it now matches what f of negative x was, so this is in fact odd. Now the shortcut to visually seeing if a function is odd is if we take the function, so in this case x to the fifth plus x. If you can rotate this 180 degrees, then this is going to be, and it looks the exact same as the original, then this is going to be an odd function. So what we're going to do is, if you were able to take your calculator and you took this picture, and if you take your calculator and you're able to turn it upside down and it looks the same, it's an odd function. So if I can paste this in here, this is kind of the way I can visually show this to you. And let me shrink it down a little bit. If we took this and I flipped this upside down and it looks the exact same as the original, that is an odd function. Okay. You guys have your calculators, you could, or your laptops, turn them upside down. If it looks the exact same, it's an odd function. All right. Last but not least, what happens if it is a neither situation? Well, a lot of people want to say, oh, just because something has a squared term, it's even, or a cubed term or an odd term, it's odd. That's not the case, and E is going to be the perfect example of that. This one is not going to be even because when we plug this in, we end up with negative x squared minus 2 times negative x minus 8, which simplifies to be this, right? This plus sign is not the same as this minus sign, so it's not even. Right, so again, do not just go off of the square term. A lot of people want to make that mistake. This is not even, so this is not working out. Well, if we check if this is odd, okay, we have negative f of x. So if we take that original function and we negate it, negative x squared plus 2x minus 8, because we don't have to check this here. Notice, oh, excuse me, this should be plus 8. Notice, again, this is not the same as this, right? The f of negative x did not equal negative f of x like we talked about. It has to here. These two did not match. So this is not odd. This is a neither situation. And just to confirm the neither situation, if we were to graph this here, so we have x squared minus 2x minus 8. There is not symmetry right now to the y-axis, so it's not even. And if we flipped this computer upside down, it would not look the exact same as this, right? It would be downward facing, so it's not odd. And so that can kind of confirm for us that. Now, again, visually is probably honestly easier to identify than all of these, because if we look, for instance, for things like absolute value of x, if we type these in, I'm missing where my little calculator thing is, value of x. Here we go. This is even because we could fold it over the y-axis, so we could see that it is that this is even, right? It's got that symmetry versus number or letter A on this example. This is neither, because there isn't symmetry. I can't fold this over the y-axis and it look the same. And if we flip this upside down, it's not going to look exactly the same because this is not passing through the origin. So you really want to look for things passing through the origin for it to even have a shot of being an odd function. Okay. All right. Last little bit then to talk about here on the last page here. If we want to talk about something being an even function versus an odd function, if we want this to be an even function, again, we need to have that symmetry over the y-axis. So all of these values would have to reflect over and be the same at the opposite x values. So for instance, if we have positive 2, this would have to be at 11. So that if it was at negative 2, 11, it's at positive 2, 11 over here. Or if this was at 1, 2, this now needs to be at negative 1, 2 to see that relationship. So negative 5, 578, negative 9, 6402. Okay, because it needs to reflect over that. Versus here with the odd functions, a reminder, we want this to be true, right? We want this, the negative x versus negative f of x. So again, what this means is basically a rotation of 180 degrees, aka you're changing both your x and your y values signs. So whatever signs they were, these now need to flip-flop to get that rotation of 180 degrees. So rotate 180 degrees, it turns into your x and your y values switching both of your signs. I know a lot of you have not seen this probably since geometry. That's what has to happen for this to be able to rotate and be true. Okay. Okay, and then just talking about which transformations will maintain the symmetry of an even function. Well, if we have an even function, for instance, x squared is an even function. Everything is going to maintain symmetry except a horizontal translation. Any horizontal translation, so minus 2, we square this. This is not going to maintain symmetry because now we are not reflecting over that y-axis, right? So everything, all the other transformations, but horizontal translations will maintain the symmetry. The ones for odd functions then, so if we talk about, for instance, to the third power, this would be an odd function. Normally the parent function would be, well, again, we're not passing through the origin anymore, right? This is not going to be a rotation of 180 degrees anymore. So horizontal translations also will change the symmetry of odd functions. And the other thing you have to be careful for with odd functions is vertical translation. Because again, it's no longer passing through the origin, so it's no longer going to be able to be rotated 180 degrees. And the origin is kind of the special thing here. So everything in this case, but horizontal and vertical translations, right? Again, it goes back to moves from the origin. You're not passing through the origin, you're not odd. Origin, odd, put them together, okay? All right, last but not least, There's a lot more practice in this, but I think this is an interesting fact. There's only one function that is both even and odd. What is it? And that is f of x equals 0. This is the only function that's going to be both even and odd, because if I plug in negative x, 0 worked, and negative f of x is 0. So if we just graphed this, if we just had f of x equals 0, it's because it's a horizontal line. There's 0 symmetry there, no matter which way you look at it. So if you have not had the chance to, I would highly recommend getting this getting these jotted down from that first page somewhere, just or at least having that initial page of the notes handy at some point on page 77 to kind of know what all of these mean, and then kind of our other vocabulary words of the day: parent function, even function, and odd function. Okay. Thanks everyone. Sorry for the long lesson. Have a good one.